Hi there, friends. We're going to finish up Chapter 5 today by talking more about the fundamental theorem of calculus. We're working with that a little bit more, and then that will bring Chapter 5 to its conclusion. All right. So let's start with the definition of an integral. So an integral takes the f prime, makes it an f, and then we plug in the upper bound and the lower bound. Okay, so let's establish we've been talking about that for quite a long time. So let's suppose now that f of a can be replaced with c as a constant, but b is still unknown. So then this would become a to b of f prime of t dt equals f of b minus c. And if we're trying to find b as our unknown, we would want to get it alone. We want to get that by itself. So I'll add c to both sides. So I end up with c on the other side plus a to b of f prime of t dt. And that equals regular f of b. So it is helpful sometimes to be able to rearrange and move things around to your advantage. And so here's a situation now, okay, if what you're trying to find is little b, then start working towards getting it alone by moving things around. So then we have this new definition that f of x alone can start with a c and then have an integral added to it. So you have to think of it like an accumulator, like a visual. Okay, so think of some function, and here's your point A. The constant c represents all of the area that exists before you get to A. Okay, that constant represents all of that area. You've already accumulated that much area. So now starting from A and going to the right, how much more area will you accumulate until you stop at a specific point? That's what this is saying, okay? You want to start with a constant value already and then continue moving forward, accumulating area as you go. So let's see how we can apply this to a new function. So find f of x if f prime of x is e to the negative x squared and f of 7 is 3. Okay, so e to the negative x squared looks like this. Okay, and we are trying, this is what e to the negative x squared. F of x is the antiderivative of that, so all of the area accumulated, and we are put up to the number 7. So let's 1, 2, 3, 4, 5, 6, 7. And so what we're saying is that all of the area before you get to the number 7, and this is only 1 unit high, so my scale is really terrible right here, but and all the way back even to infinity, that all of that is already 3, and then f of x would move forward from that. So we say that f of x is 3 plus, starting at 7, going to any other x moving to the right, of f prime of t dt. Okay, so the reason we change variables is because we can't have the same variable both here and here. Those are the x's, and so we need to pick an arbitrary variable in the function. It's just a notation thing. It's not a big deal. You could pick I wouldn't pick y, but you could pick z or w or q, or really t is just the most common variable to use. But this variable here, the choice of variable, is arbitrary as long as it's not x. And I would say stay away from y. So t is just the most common. Okay, let's try another one. So find g of x if it accumulates area under the square root of the sine of x, and we know that the initial condition is -1, 7. So g of x would already have a value of 7 at the initial condition going to any other x, and we're accumulating the area under, and I'll just do the sine of t dt again. So there's really no math for you to do other than for you to understand how to set that up. Okay, so now we're given the function f of x, whose derivative is f prime equals tangent x, which means f of x is the accumulating area under that, and we know that f of 3 equals 57. So if we want to find f of x, that means we've already have 57 units of area, and starting at the number 3, going to the tangent of t dt, accumulating from that point forward. Then now we're asked to find f of 7. Actually, that's a typo. It should be 4. Can you fix that? F of 4. So picture the tangent graph, right? And so now we want to have those 57 initial condition values, and we're going to go from 3 to 4 and accumulate some more area under that curve. So you can do a math 9 on this one, and your calculator doesn't matter, that you don't have to change it to t. Okay, when you do a math 9, just leave it as x. So do your math 9 from 3 to 4 of tangent x dx on a calculator, and that's going to give me 57 plus 0.415. So we're looking at a new value of 57.415. All right, now here's an actual graph we're going to work off of. So 2 line segments, so you're looking at an absolute value, and the function is defined this way, where g of x is defined as the accumulated area starting from 0. Okay, 0 is where you're going to start accumulating your area. All right, so the first question is find g of negative 1. So g of negative 1 would represent the accumulated area from 0 to negative 1 of f of t dt. So we're running backwards on this picture. The accumulated area from 0 to negative 1 is a triangle, but it's a backwards triangle. That means that's another way you can get negative area. If you go backwards on a graph, that value, if it's above the x-axis, would be negative area. So that's a negative triangle. And so the answer to this would be negative, well, it would be 1/2 times the base, which is negative 1, that's where the negative comes from, times 3. So you're looking at negative 3/2. The next thing we're asked to find is g prime of negative 1. Well, we have to find a formula for g prime first. So in order to find g prime, I need to introduce a d dx in front of this integral. And that d dx will negate the integral and the differential. And then we'll have f with the upper bound plugged in times the chain rule of 1 minus f with the lower bound plugged in times the chain rule of 0. Clean that up, and all you have is f of x. So in other words, g prime is the y value on the graph that you're looking at. So if we want to know, I'm going to erase just to give myself some space here. So then g prime at negative 1 would be the y value at negative 1 on this graph, and the y value happens to be 0. And then what's g double prime? Well, if g prime is f of x, then g double prime has to be f prime, which is the slope value at that point. So we're finding the area up to the point, we're finding the point itself, and we're finding the slope value. Okay, and that slope value, if I just count simply rise over run at that position, so g double prime, negative 1, rise over run is 3, up 3 over 1. All right, next question. Same figure, same definition. For what values is g increasing? G increases when G prime is greater than 0. All right, well, what is G prime? Well, remember we defined on the other page that G prime is the d dx negating that, and that turned out to be f of x. So G increases when f of x is greater than 0. Well, just looking at the graph of f, I can tell that f of x is greater than 0. It's above the x-axis. So that's happening from -1 to 1. That's my reasoning. So you could reverse the order of that. You could say G increases on -1 to 1 because G increases when G prime is greater than 0. And since G prime is equal to f of x, it would increase when f of x is greater than 0. For what values, same picture, same equation, for what values is G concave up? Well, the definition of concave up, G will be concave up when G double prime is greater than 0. Well, what was G double prime? Well, remember that G prime is f of x, so G double prime has to be f prime. So then we could say G is concave up when f prime of x is equal to 0, which is the slope. Not equal, greater than, sorry. F prime of x is greater than 0. So I need to look for positive slope on this graph. Positive slope is happening on this region. And so from -2 to 0. Trust your definitions. Write it down, okay? Write down what I know it's concave up when this happens, and then figure out the expression as they are related by definition. Okay, let's try another one. Here's a new picture, new graph. Find all intervals for which G is less than 0 for this picture. Well, what is G? Okay, G is the accumulated area starting at 2 under this picture. So my question is, when would accumulated area be negative? Starting at 2. Well, it's going to be negative as long as I go backwards. There's negative area. There's more negative area. So far, I've accumulated a whole bunch of negative area. Now, if I keep going beyond that, okay, that area that this little section, that's negative. Is it enough negative to entirely cancel out the I'm so sorry. The green triangle is positive now. Why is it positive? Well, because I'm going backwards and I'm below the x-axis, so it's a double whammy, it's a double negative. So this is positive area right here. But what's the accumulation? The accumulation is all of that grouped together from 2 backwards. And so that is a bigger negative area. So this part is all negative. The accumulation of that is still negative. There's still more negative than positive. And even if I go all the way to the end here, that's more positive area, but it's not enough area, positive area, to accumulate with the negative. So it would be negative the whole way through. So it would be negative from -4 all the way to 2. All right, how about going the other direction? How about going forward? So I'm going to erase this a minute so that we have a clean slate. Okay, starting from number 2, the number 2 and moving forward. Okay, if I go, this is all positive area. Once I cross the border, this is negative area. Now so far, if I only go up to number 9, there's still more positive area than negative area. So the overall accumulation is still positive. When I finally get to the number 10, there's a complete canceling out of the positive area and the negative area. So when I go beyond 10, now I'm accumulating more negative area than positive area. So from 10 to 12, I also will have a negative accumulation. Same picture. Find the absolute maximum and absolute minimum. Okay, go to the definition. A max for G occurs when G prime changes from positive to negative. Well, what is G prime? Well, G is the accumulation, so G prime would be the derivative, which cancels out the integral. So f of x times the chain rule of 1 times f of 2 times the chain rule of 2, chain rule of 2, which is 0. All of that cancels itself out, so I am left with G prime being equal to f. So I can add that to my statement. A max for G occurs when G prime, which equals f, changes from positive to negative. So I need to look at this graph and find out any time it changed from positive to negative. And I only see that happening once. So that is at x is 6. Now how about a min? Oh, but we want absolute. Oh, good. I'm glad I read my own work. Absolute means I also have to check the endpoints. Okay, could the endpoints be a positive? So, or at x is -4 or 12. So which one would be the absolute? So now we actually have to count up the accumulated area at each point. So what would the accumulated area at G -4 be? What would the accumulated area at G of 6 be? And what would the accumulated area at G of 12 be? Okay, let's talk about accumulated area. So let's do G of -4. If I start going from 2, accumulating area back to -4, remember that that's all negative. And even though I start creeping up with some positive values here, it's still not enough. It's a negative number. I don't think that's going to be an absolute max. If I do to 6, right, well, that's all positive because I'm moving forward. And then what if I go beyond 6? Keep going. Well, remember that this is negative, but the overall accumulation is still positive, but it's going down. It's getting less, and by the time I get to here, it's 0. And now I'm getting into even more negative territory. So that's going to be negative also. So the absolute is indeed happening at G of 6. All right, if we want to do minimum, we just flip the script on here. So let me erase a bunch of this. Okay, just change my words, and I can redo the same thing. So the minimum for G occurs when G prime, or F, changes from negative to positive. All right, well, where does that happen? Okay, where on my graph am I changing from negative values to positive values? Get all this erased. Okay, well, I see that I'm changing from negative to positive here. And there's no other place where I'm changing from negative to positive. So it's either at x is negative 2 or at x is negative 4 or 12, the endpoints again. Okay, where is there going to be the most negative? So I need to check, again, g of negative 4, g of negative 2, and g of 12. All right, so accumulating my negative area. So going back this way, right, that is definitely negative area because I'm running backwards. In fact, how much negative area am I getting? Well, it's a triangle, so 1/2 of negative 4 times 4, so that would be negative 8. Then I'm going to have some positive area to accumulate into that total, which is 1/2 of the base of negative 2 times negative 4, so that's overall positive 4. So my accumulated, okay, so remember this is negative 8, this is positive 4. Then let's move forward, positive area here, positive 8. Negative 8. And more negative 4. So altogether, accumulating that, moving to the right, that gives me negative 4 also. So the absolute is going to happen here. That is the lowest of that. Okay, what is happening at 10? Okay, do you have a relative min, a relative max, or neither? At 10, justify your answer. All right, well, we need to know what kind of a change is happening at 10. What is G prime doing? G prime is F doing at x is 10. Well, G prime, which is equal to F, is negative, staying negative, never crosses the x-axis. So since G prime equals F, stays negative around x is 10, then x is 10 is neither a max or a min. All right, I think this is the last one on this question. What's happening at 4? And we were talking about point of inflection. All right, well, we need to know then, we need to answer the question, what is G double prime, which is equal to F single prime, doing at x is 4? So at this position right here, what is the slope doing? Well, the slope is changing from positive to negative. So the values of G double prime, which is equal to F single prime, are changing from positive to negative. So x is 4 is a point of inflection. So always go back to asking yourself the question, what do I need to show in order for it to be a max or a min or a point of inflection or increasing or decreasing? Let's try a different graph. All right, the figure shown is the graph of a differentiable function. The particle moving along the line is defined, so this is f, the graph is f of x. The particle moving along the line is defined as s of t is the accumulation starting at 0. So the meaning of the defined function of t is that the position is found by the accumulated area starting at 0. So what would the, oops, I missed a letter. What would the velocity and the acceleration functions be and their meaning? Well, velocity would be the derivative of the integral. And we've done this a couple times now. So I get f of t. F of t is the graph itself, so that would be the y value. And then the acceleration is the derivative of the velocity, which is f prime of t, which will be the slope value. So again, if you're reading this graph, position is area, velocity is y value, the height, and acceleration is the slope. So asking ourselves a couple questions. What is the initial position? So s of 0. So what is the accumulated area starting at 0? Well, it's 0. When you're at 0, you haven't accumulated any area yet. What is the position of the particle at 3? So that would be the accumulated area starting at 3. The accumulated area is beneath the x-axis. It's a rectangle. The rectangle has area of -9. So the position of the particle is -9. So the initial position was 0. Now the initial position is -9. So when will the particle return to the origin? Well, it's got to make up the negative area that it just accumulated. So the only way to do that is to accumulate an equal amount of positive area. So once I get an equal triangular shape, it would be at time equals 6. Same figure. When is the particle moving toward the origin, and when is the particle moving away from the origin? Toward the origin would be positive velocity. Away from the origin, other way around. Toward the origin would be negative velocity. Well, you have to compare the position, I guess. Moving towards or away, we have to know the position compared to the velocity. Okay, the position compared to the velocity. So it's important to know when this has positive position and when it has negative position. So from 0 to 3, the position is negative. That's the area that we accumulated. From 3 to 6, although the area from 3 to 6 is positive, the accumulation is still negative until we get to, right up until the point we get to 6. Once you get beyond 6, from 6 to 9, you've negated your area, basically a clean slate, and so now this area, the accumulated total, will be positive. Now we got to compare that to the velocity. The velocity are the y values of the graph. So between 0 and 3, the y values are negative. Between 3 and 6, the y values are positive. And between 6 and 9, the y values are positive. All right, so when is the particle moving toward the origin. You move toward the origin when the position signs and the velocity signs are opposite. And so the only time that would move toward the origin would be this section because they have opposite. Away from the origin is when the signs of the velocity and the position are the same. So that would be both 6 to 9 and 0 to 3. On what side of the origin does the particle lie at time 9? Well, at the end of time 9, I have positive position and I have positive velocity, and so I'm on the positive side of the origin. All right, last one. What is the velocity of the particle at time 3? Well, the velocity is simply the y value at time 3, and the y value is 0. Units per time, whatever our units are. What is the acceleration of the particle at time 3? Well, that's going to be the slope value, so I simply determine the rise over run, which I believe we're looking at in that section. Oops, I could write this down. A of 3. A rising value of 12 over a running value of 6, so we're looking at 2. And what does that mean about the particle's movement? Okay, so now compare the velocity and the acceleration at time 3. The velocity is 0. That means it's stopped. The acceleration is 2, which means it's moving forward. Okay, so it's stopped, but in the process of moving forward. We could say maybe facing or moving forward. And it's also going to be getting faster, speeding up. Let's use those words since we've been using those before. All right, so your work is cut out for you in terms of reading and understanding all defined functions defined as starting out as an accumulator function. So when you define something starting out as an accumulator, everything kind of trickles down from there. Okay? All right, so we will come together on Tuesday as a review day. Wednesday would be a review day. If you want to come in or schedule an extra Zoom time, if you've got more questions on either of those days, I could be available to you. And then Thursday, we'll take our test on Chapter 5. All right, so I hope you have had a good weekend and a good start to the rest of your week. All right, see you tomorrow.